Today we are looking at biological molecules. We'll start with carbohydrates, monosaccharides, the simple sugars. Like in chemistry, all monomers form polymers, and here we have monosaccharides forming a two-sugar disaccharide and finally a long-chain polysaccharide, complex carbohydrates. The most famous of these monosaccharides is glucose. As you can see here, glucose comes in two isomeral forms, alpha and beta glucose, no positions of the hydroxyl groups on carbon 4. We need to know about fructose, glucose, and galactose, the three monosaccharides. As you can see here, from glucose, a structural isomerization occurs to form fructose, moving the C to bond O, and in galactose, it is a stereoisomerization, a rotation of the hydroxyl group on one of the central carbons. In this video, we are looking at biological molecules, carbohydrate, disaccharide. From the previous video, we know about glucose. We know there are two forms of glucose, alpha and beta. Again, know the position of the hydroxyl groups. We also know that there are three monosaccharides, glucose, fructose, and galactose. Now, if these monosaccharides were to bind together, they would form a disaccharide. Condensation reaction would remove water, and we would have what is called a glycosidic link. The three disaccharides we need to know are displayed here. The first of these is sucrose. Sucrose is glucose plus fructose. The second one is lactose. Common sense, galactose and glucose forms lactose. And finally, maltose sounds like Maltesers, pure sugar, glucose plus glucose. Here you can see all three of these disaccharides laid out. This video is looking at biological molecules, carbohydrate, polysaccharide, the complex carbohydrates, bread, pasta, etc. Now remember from video 1 and 2, glucose is the base unit of a monosaccharide. Also recall, alpha and beta glucose are isomeral versions, position of the hydroxyl group. Once these two monosaccharides join together, they form a disaccharide with a glycosidic link or a glycosidic bridge. Because of the shape of the glucose ring, there are 1, 2, 3, 4, 5, 6 carbons. Therefore, bonds can form in a glycosidic link in a 1,4 glycosidic bond or a 1,6 glycosidic bond, as shown in this diagram. The first of the polysaccharides we will look at is starch. Now, starch actually consists of two different polysaccharide chains. There is amylose and amylopectin. Amylose, as I remember, a short word, so it is a relatively long continuous molecule, combined from 1,4 glycosidic links, as shown in the diagram. Amylopectin, a relatively longer word, has short chains, i.e. it is not very long before reaching a 1,6 bond to form branches. Amylose is a long, straight, continuous 1,4 glycosidic bonded molecule. Amylopectin is a 1,4 glycosidic molecule with frequent 1,6 bonds to form side chains and cross linkages. Animals require a higher metabolism than plants, and therefore a much more branched molecule, i.e. quicker to metabolize, is required. Glycogen has the same 1,4 glycosidic bonds, but it is significantly more branched with 1,6 bonds. The final polysaccharide to look at is cellulose. Now, cellulose differs in that it has beta glucose bonds as opposed to alpha. As you can see from this diagram, these beta bonds enable an inversion, i.e. a flipped AB-AB structure. As you can see here, this enables cellulose to have very tightly packed fibers or microfibrils. As you can see from this diagram, this enables cross-hydrogen links. This makes cellulose extremely strong. Cellulose is, of course, a structural polysaccharide.